So as Adam mentioned, my research was basically a paleoceanographic and geochemical analysis of the late Ordovician and early Silurian. So when I first came to Cal State Fullerton from the great state of New Jersey, I met with Adam. And Adam had done a lot of work in the Triassic, and I kind of assumed that I'd also be doing a lot of work in the Triassic as well. And when I first met with Adam, Adam kind of proposed the idea of working in the Ordovician. And my first reaction was, the Ordovician, I wanted to work on something older, like the Triassic. And then I had to sit there for a second, think about the time scale, and I realized that the Ordovician was older, and I was on board. But then I had to remember, well, what was going on in the Ordovician? What makes this Ordovician so interesting and so fascinating? And it turns out a lot. So the Ordovician was a really interesting and dynamic period of time. So to start, the paleogeography of the Ordovician was a lot different than it is today. We have Laurentia, which is modern-day North America. This was positioned at the equator and rotated roughly about 90 degrees. We also have the formation of a supercontinent known as Gondwana, and this consisted of South America, Africa, Australia, and India. And this was positioned over at the South Pole. The northern hemisphere during this time was essentially void of any large land masses. So all the action was going on in the southern hemisphere. Sea levels during this time were either near or at their Paleozoic maximum. So this flooded the Laurentian Craton and created a shallow Epiric Sea and led to the widespread deposition of carbonates along the Laurentian Craton. And it's also worth noting that the Ordovician was a greenhouse world. So atmospheric carbon dioxide levels were 10 to 14 times higher than present atmospheric levels, and some even estimated that they were even higher, up to 16 times higher. So despite being a greenhouse world, the late Ordovician saw a period of dramatic climate change. So we experienced a period of global cooling. This global cooling led to the Hernanian glaciation. Now, Hernanian glaciations were the first major glaciation of the Phanerozoic, and these were a large glaciation that occurred on the supercontinent of Gondwana. The extent of glaciation either matched or exceeded the glaciation that occurred during the Pleistocene. However, the onset and termination of this glaciation during the Hernanian, the latest Ordovician, was a lot more rapid. So we went very rapidly going from a greenhouse world into an icehouse world. And then when the glaciation terminated, it went very quickly back from an icehouse back to a greenhouse world. However, the duration of this glaciation is still debated. So some argue, such as Finnegan et al., that it was a rather short-lived glaciation that only lasted throughout the Hernanian and was limited to about 500,000 years. While others argue that this was a longer, more protracted glaciation that stretched through the late Ordovician and into the early Silurian, and that this lasted about 10 million years. And the longer hypothesis was proposed by Saltzman and Young. Whether it was short-lived or long-lived, the Hernanian glaciations had very dramatic effects, and one of them being the end Ordovician mass extinction. So this is one of the big 5 mass extinctions. It's the first of the big 5 mass extinctions. And it's worth noting that it's the only of the big 5 mass extinctions that coincides with a glacial event. 85% of marine fauna went extinct during this time. So this was a very large mass extinction, and it was actually the second largest mass extinction, only second to the end Permian mass extinction. And this extinction occurred in 2 phases. So there was an initial phase that occurred during the onset of glaciation, and then a second phase of extinction that occurred at the termination of glaciation. The first phase of the mass extinction is generally attributed to climate deterioration with the onset of glaciation on Gondwana. The second phase of the mass extinction, the mechanism is a little bit debated. Some argue, such as Finnegan, that this is also attributed to climate deterioration, that the cold water fauna of the Hernanian were adapted to colder water environments, and that when glaciation concluded, we go back to warmer temperatures, and this cold water adapted fauna go extinct as the climate warms up. Others argue that the second phase of the mass extinction was actually attributed to widespread anoxia, which coincides with the widespread deposition of black shales along the margin of Gondwana during this time. Another effect of Hernanian glaciations is the HICE, which is the Hernanian isotopic carbon excursion. So this is a large positive isotopic excursion that reaches about 3 to 7 parts per mil. Now, the HICE is important because the start of the HICE coincides with the onset of glaciation on Gondwana and the first phase of the mass extinction. The end of the excursion coincides with the deglaciation of Gondwana and the second phase of the mass extinction. So the HICE provides a stratigraphic marker for these events. So when we see the onset of this excursion, we know that we have glaciation occurring, and we see the first phase of the mass extinction. When we see the end of the excursion, it's that stratigraphic marker for the end of the mass extinction and the end of Hernanian glaciations. The HICE has been documented throughout Canada, Scotland, Siberia, Nevada, other places such as China, and it shows that the HICE is not only an excellent stratigraphic marker, but it's also a worldwide phenomenon. So this is an excellent tool to date and use when we're looking at Hernanian strata. And another final hypothesized effect of Hernanian glaciation is increased upwelling and vigorous ocean circulation. So this model is after Brenchley et al. In 1995. And what we see is that when we have no continental glaciation, so such as the middle to early Ordovician, we see more sluggish ocean circulation. And this is attributed to a more stratified ocean based on temperature and density. However, in the late Ordovician, the Hernanian, we see the establishment of glaciation on Gondwana. What this does is we're going to see a decrease in sea level, but we're also going to see the downwelling of cool waters along the margin of Gondwana. This downwelling along the margins of Gondwana is going to increase ocean circulation, which is going to bring up nutrient-rich cold water along the margins of Laurentia. This nutrient-rich cold water is going to commonly lead to the formation of algal blooms. So even though deglaciation was transpiring at the South Pole, the effects are still going to be noted over along the equator. Previous work has been done by Pope and Stefan 2003 and Pope 2004, and they examined chert-rich carbonates and chert-rich shales deposited in the late Ordovician along the southern margin of Laurentia. Based on their analysis of these chert-rich carbonates and shales, they were able to definitively say that upwelling was occurring along the southern margin of Laurentia. And they hypothesized that the correlative chert-rich carbonates and shales along the western margin of Laurentia were evidence for upwelling during the late Ordovician along the western margin as well. However, these rocks have not been subjected to a detailed paleoceanographic analysis. So that's where I come in. So the first objective is to test this hypothesis of Pope and Stefan and to determine if upwelling was indeed present along the western margin of Laurentia during the late Ordovician and into the early Silurian. Once we determine if upwelling was indeed occurring along the western margin, we'd use that as a proxy for how long the duration of glaciation on Gondwana persisted. So if we see evidence for a long-lived upwelling and long-lived vigorous ocean circulation throughout much of the formation, this would suggest that the Hernanian glaciations were also long-lived and support the hypothesis of Saltzman and Young of a long-lived glaciation stretching into the early Silurian. However, if vigorous ocean circulation and increased upwelling were a short-lived phenomenon only seen throughout a small portion of the Ely Springs Dolomite, this would suggest that the Hernanian glaciations were also short-lived, supporting the hypothesis of Finnegan et al. The next objective is to examine the oxygen levels along the western margin of Laurentia during the late Ordovician. And then to determine the effect of oceanographic changes, so changes in ocean circulation, changes in the outboiling of nutrient-rich waters, changes in oxygenation levels, and what effect those had on marine fauna from before, during, and after the end Ordovician mass extinction. So how will this be accomplished? Through the use of the Ely Springs Dolomite. So the Ely Springs Dolomite provides a means to examine these paleoceanographic changes throughout the late Ordovician and into the early Silurian. So a little bit about the Ely Springs Dolomite. The Ely Springs Dolomite is exposed throughout east central California and throughout Nevada. We examined 2 localities in the Owens Valley region, just west of the Inyo Mountains and Death Valley. The first location that we examined was Willow Springs Canyon in Mazorca Canyon. And the other one was White Swan Mine, located in the Talc City Hills. Talc City Hills is a more shallow water environment compared to the more deeper water Willow Springs Canyon. The Ely Springs Dolomite conformably overlies middle Ordovician quartzite. So at White Swan Mine, it overlies the Eureka quartzite. At Willow Springs Canyon, it overlies the correlative Johnson Spring Formation. The Ely Springs Dolomite is then overlain by early Silurian carbonates. So the Hidden Valley Dolomite at White Swan Mine and the Von Gulch Limestone at Willow Springs Canyon. The age of the Ely Springs Dolomite was determined in 1975 by Miller, and he used conodonts in order to determine the age. He observed Ordovician age conodonts in the basal portion of the formation and Silurian age conodonts in the upper portion of the formation. And then the formation itself is divided by Ross in 1966 into 3 informal members. The lower member consists of a dolostone with chert beds and chert nodules. It's a very chert-rich member. The middle member, we see the disappearance of chert. So this is a massive dolostone. And then the upper member, we see the reappearance of chert, and it's a very chert-rich dolostone once again. And we see the occurrence of these thick chert beds at Mazorca Canyon, Willow Springs Canyon. So the methods that I'm going to use, or used, was one, I examined sedimentological features. So, for example, measuring strat columns, looking at different features within the lithologies, and looking at fossil assemblages. Did an isotopic analysis, in particular, measured del carbon-13 values throughout the formation. Analyzed major and trace elements. Analyzed total organic matter. And then analyzed some of the data using some statistical methods. So sampling was done, obviously. So at Willow Springs Canyon, a total of 84 samples were collected throughout the Ely Springs Dolomite and into the basal portion of the overlying Von Gulch limestone. A total of 69 dolostone samples were collected. They were collected at an interval of every 1.5 meters. 25 chert samples were also collected at the Willow Springs Canyon locality. They were collected with every 3rd dolostone sample, so roughly at every 4.5 meter intervals. At White Swan Mine, 37 samples were collected. They were collected at irregular intervals in order to analyze sedimentological changes or noting interesting lithologies. And 14 of those were slabbed and polished. And I should note that 6 samples also from Willow Springs Canyon were also slabbed and polished to analyze sedimentological features as well. And then a total of 49 thin sections were made, 32 from White Swan Mine, 17 from Willow Springs Canyon. The 69 dolostone and 25 chert samples that were collected from Willow Springs Canyon were brought back. They were then trimmed using a trim saw in order to remove any weathered surfaces and in order to remove any veining that occurred within the sample. They were then powdered using a steel ball and mill in order to be analyzed. So the 69 dolostone powdered samples were analyzed for their del carbon-13 values. So These were analyzed in the lab of Dr. Sean Lloyd. The procedure we used was 5 to 8 milligrams of the powdered dolostone samples were first weighed and then placed in a vial. The air within the vial was then vacuumed out of that to remove anything in there, and then 3 milliliters of phosphoric acid were added into each vial. The phosphoric acid and the powdered dolostone samples were then left overnight in order to react and produce carbon dioxide gas within the vial. The carbon dioxide gas that was then produced was then analyzed using a Picaro cavity ring down spectrometer through an automated carbonate preparation system. And this analyzed, once again, for the del carbon 13 values. Each sample was analyzed 3 separate times in order to determine the reproducibility of each sample, as well as 2 lab standards were used, a Dolomite lab standard and a calcium carbonate standard, in order to determine any drift through each run. Geochemical analysis was also completed. This was completed on both the dolostone and chert samples from Willow Springs Canyon. Approximately 50 milligrams of the powdered sample were digested, hence the stomach. And they were using a cocktail of acid, which was nitric acid, hydrochloric acid, and hydrofluoric acid. So this mixture of acid was added to each sample. They were then placed in an Anton Par microwave and heated up in order to react, and then cooled to room temperature. Once these samples cooled to room temperature, a second round of digestion was completed, and this was using a mixture of boric acid and hydrogen peroxide. They were placed back inside the microwave, heated up, cooled once again to room temperature. So once these samples were then cooled to room temperature, they were weighed, diluted to 50 milliliters, and then they were analyzed using the ICP-OES, the inductively coupled plasma optical emission spectrometer, housed here at the Geology Department of the Cal State Fullerton in the lab of Dr. Adam Woods. The ICP-OES measured for major elements. In particular, we analyzed for aluminum, calcium, potassium, magnesium, manganese, sodium, phosphorus, silicon, and titanium. Aluminum and titanium were both used as proxies for detrital input. We also analyzed for trace elements. So trace elements, we analyzed the composition of barium, copper, nickel, and zinc. And these elements were used in order as a proxy for primary productivity during this time. And here's primary productivity occurring off the coast of New Jersey. Just want to point that out. Once the barium, copper, nickel, and zinc concentrations were determined, the enrichment factors of these 4 elements were then determined using this equation here. So the enrichment factor for barium, for example, the barium concentrations for a sample were divided by the aluminum concentrations for the same sample, and that was to remove any detrital signature. That was then divided by the barium concentrations and the aluminum concentrations for a standard. The standard that we used was world average carbonate values from Turakian and Wiedipol, 1961. Zircon concentrations were also measured, and along with aluminum and titanium, they were used as a proxy for detrital input. And uranium and molybdenum were used in order for the determination of paleooxygenation levels, oxic, disoxic, anoxic, or euxinic. Loss on ignition was completed on the 69 dolostone and 25 chert samples from Willow Springs Canyon. This was done using the method described by Dean, 1974, and this was done in the lab of Dr. Matthew Kirby. This was completed by first weighing samples in a pre-weighed crucible. The samples were then heated up to approximately 100 degrees Celsius for 1 hour. This was in order to determine the dry weight. So samples were then re-weighed, heated up to 550 degrees Celsius for 2.5 hours, and this was to determine the weight after 550. Samples were weighed one final time, and the dry weight, we subtract the weight 550 from it in order to determine the total organic matter within each sample. So at Willow Springs Canyon, what we see is that the lower member basically consists of a chert-rich dolostone unit. The dolostone is a light gray dolomudstone with very thinly layered laminae. Black chert beds and chert nodules occur throughout this formation, as seen in this picture here. At the top, or the uppermost portion of the lower member, we start to see the disappearance of this chert, and we start to see wavy bedding, indicating a possible decrease in sea level. This is then followed by the establishment of an oncolytic dolopaxstone. This oncolytic dolopaxstone indicates that we have higher energy depositional environment, also supporting that we have a decrease in sea level during this time, leading to the formation of oncoids. This oncolytic dolopaxstone unit is overlain by a brecciated layer. This brecciated layer, or actually in some outcrops, the brecciated layer occurs above the oncolytic dolopaxstone. In other outcrops, the brecciated layer occurs as discontinuous lenses within the oncolytic dolopaxstone. This brecciated layer has been interpreted by Dornfest as a paleokarst layer due to a drop in sea level. The middle member, we see the disappearance of chert, and we see a massive dolomudstone. Bedding is either absent or difficult to determine throughout this member, indicating that intense bioturbation was going on throughout the deposition of the middle member. A sequence boundary placed by Dornfest 11 meters above the base of the middle member occurs here. And then we transition to the upper member. The upper member, we see the reappearance of chert, once again occurring as black chert nodules and chert beds. However, we also see the occurrence of two thick chert beds. So this here is a 2-meter thick chert bed, and then there's also a 9-meter thick chert bed that occurs near the very top of the formation as well. The fossils that we see at Willow Springs Canyon, we do see some solitary isolated rugose corals. These occur in the lower member, and we also found a few isolated rugose corals at in the middle member. These were identified as streptolasma, and they were not found in life position. So these were believed to be brought in by a storm event. In thin section and in hand sample as well, we see abundant crinoid ossicles, and these occur throughout the entire formation, throughout all three members. And we also see what may or may not be in this picture, a sponge spicule. So sponge spicules were believed to be the source of silica for the chert-rich lower and upper members. As I stated earlier, the age of this formation was determined by conodonts, by Miller in 1975. He observed Ordovician-aged conodonts throughout the lower member and Silurian-aged conodonts in the upper member. However, the middle member was a conodont barren zone. So Miller placed the Ordovician-Silurian boundary in an undetermined stratigraphic marker within the middle member within this conodont barren zone. Member resembles the lower member at Willow Springs Canyon in the sense that we have a light gray dolomudstone that has chert nodules and chert beds. And we see a mottled bedding near the top of the lower member. This is indicating that we have bioturbation going on, possibly indicating that we have a decrease in sea level towards the top of the lower member. We have a few scattered isolated oncoids that occur near the top of the lower member. We don't see the establishment of a oncolytic dolopaxstone like we see at Willow Springs Canyon. So we believe that these may be brought in from further up on the shelf. And then we see the occurrence of thick, this is a 15 centimeter thick crinoid hash bed. So the presence of these thick crinoid hash beds and these oncoids all indicate that we do have a decrease in sea level towards the upper member. Or towards the upper portion of the lower member, sorry. The middle member also resembles the middle member at White Swan or Willow Springs Canyon, that we have a massive light gray dolomudstone where bedding once again is either absent or difficult to find. The sequence boundary placed by Dornfest occurs 3 meters above the base of the middle member here. And then we transition to the upper member, where we have the reappearance of chert. However, the occurrence of chert within the upper member at White Swan Mine is a lot less abundant compared to the other location, Willow Springs Canyon. So chert only occurs in a few scattered places and not that abundant. We also don't see the deposition of these thick chert beds like we did at our other location. Fossils that we see at White Swan Mine, same as Willow Springs Canyon, we see abundant crinoid ossicles scattered throughout the formation, throughout all 3 members. A few isolated Streptolasma rugose corals that occur. Once again, these are not found in life position and thought to be brought in by storm events. And we also found a few brachiopods located near the very base of the lower member. So the depositional model that we have made for the Ely Springs dolomite is that during the lowermost portion of the lower member, this is the early Cadian, we see that sea levels were elevated. So once again, they were at or near their Paleozoic maximum. The depositional environment of the Ely Springs dolomite is interpreted as an outer ramp to middle ramp environment. And this is due to the chert-rich nature of the lower member, the thinly bedded nature of the dolomudstone, and the occurrence of these storm-derived rugose corals. In the uppermost portion of the lower member, we see a decrease in sea level during the late Cadian, and this is due to a global sea level regression. This global sea level regression resulted in these thick crinoid hash beds at White Swan Mine, the occurrence of wavy bedding at Willow Springs Canyon, and the modeled bedding at White Swan Mine, indicating that we do have increased bioturbation going on during this time, and then the disappearance of chert. We also proposed the migration of an oncolytic shoal that may have existed somewhere between these 2 localities and migrated towards the ocean or towards the basin as sea level dropped, which led to the formation of the oncolytic dolopaxstone and subsequent paleokarst layer that we observe at the Willow Springs Canyon locality. All right, as sea levels remained low, the oncolytic shoal continued to migrate towards the basin, and this created a semi-restricted shallow water lagoonal environment. This is indicated by the absence of chert and the massive bedding of the middle member, which indicates that we have intense bioturbation going on throughout this time. And this, we also see evidence for increased upwelling during the deposition of the middle member during the Hernanian, which I'll go over a little bit more when we talk about the trace elemental data. And then finally, the upper member was deposited in the Landoveri. This is the earliest Silurian. We see that sea levels rise once again, and we see that we have the widespread deposition of chert, including these thick chert beds at Willow Springs Canyon. And we assume that this is a deeper order based on the chert-rich nature of the upper member and the lack of fossils. The isotopic analysis that we see, so this is our isotopic data right here. At Willow Springs Canyon, we note that the lowermost portion, or the lower member and the lowermost portion of the middle member has negative values that average negative 0.3 parts per mil. A positive del carbon-13 excursion occurs within the uppermost portion of the middle member and reaches a value of 1.6 parts per mil before going back to more negative values in the upper member. This excursion is interpreted to be the HICE, the Hernanian isotopic carbon excursion, that stratigraphic marker. And using this stratigraphic marker, we are able to more definitively place the Ordovician-Silurian boundary at 66 meters right there at the base of the, sorry, not 66 meters, but right here at the base of the middle and upper member. So this does agree with the data, the Conodont data from Miller 75, who once again placed it somewhere within the middle member in this Conodont barren zone. The Heist, however, as I mentioned earlier, typically reaches values of 3 to 7 parts per mil. However, we only see the excursion reach a magnitude of 1.6 parts per mil at the Willow Springs Canyon locality. And this is due to 3 possibilities. The first of these possibilities being that exposure of the platform either led to non-deposition or erosion of part of the isotopic curve. However, the sequence boundary noted by Dornfest and the paleokarst layer over here occur below this excursion. So this makes it rather unlikely that part of the excursion is missing due to non-deposition or erosion. In addition, the excursion isn't truncated, which is what we'd expect it to appear, as if part of the excursion was missing. So this possibility is not likely. The other possibility is that Brenchley noted that isotopic profiles from down-ramp settings typically can display profiles that have complete isotopic profiles but have relatively smaller magnitudes. This is confirmed by work done by Ripperdan 2001 on the Ely Springs Dolomite in the Nopon Range. And he noted the occurrence of the Heist, and it only reached a magnitude of 2 parts per mil at that location. And the third possibility is simply that our sampling was just not at too low of a frequency in order to capture the entire magnitude of the excursion. So moving on to the major elemental data, the next few graphs that I'm going to show you are all going to look very similar to this. The blue lines represent our dolostone samples. The black dashed lines represent our chert samples. Chert didn't occur within the middle member, so that's why we don't have any chert data within the middle member. The green line here represents the oncolytic dolopaxtone layer, which was not sampled for elemental analysis. And then the gray box here represents the Heist as determined by our isotopic data. So what we see for calcium and magnesium is that calcium and magnesium stay relatively the same throughout most of the formation. However, we do see an increase in calcium and a subsequent decrease in magnesium as we transition to the Von Gulch limestone. And this is why we'd expect to see transitioning from a dolostone into a limestone. The percent titanium, aluminum, and the zircon concentrations, once again, they were used as a proxy for detrital input. And what we see is we see 2 increases in detrital input. The first one occurs right above the oncolytic dolopaxtone layer. And this makes sense that we have the establishment of an oncolytic dolopaxtone layer, indicating that we have lowered sea levels during this time, higher energy environment. And then we still have decreased sea levels, and we possibly have part of the platform to the east is still exposed and eroding sediment into the water during this time. So we do see a burst of detrital input. We see a second increase in detrital input, once again, in the Von Gulch limestone. And this makes sense as we go from the deeper water Ely Springs Dolomite into the more shallow water Von Gulch limestone. Barium, copper, nickel, and zinc. These were the trace elements that we used as a proxy again for primary productivity. And what we see is that we see a good agreement in copper, nickel, and zinc concentrations within the middle member, in particular during the Hernanian. And we also see another agreement here right below our oncolytic dolopaxtone layer. There are some peaks right there that are slightly more subdued in nickel and zinc. However, our barium, we don't see any peaks in these values over here that correspond with the peaks in copper, nickel, and zinc. And this, we believe, is due to the highly mobile nature of barium during diagenesis. So this leads barium to be enriched in other places and depleted in some places. So based on that it doesn't agree nicely with the copper, nickel, and zinc, we think that the barium concentrations within the Ely Springs Dolomite doesn't actually reflect barium concentrations during the time of deposition. The enrichment factors for barium, copper, nickel, and zinc show a similar story. So once again, we see an increase in copper, nickel, and zinc in just below the oncolytic dolopaxstone layer, indicating that we have a period of increased primary productivity. And we see a second, more protracted period of increased primary productivity during the Hernanian, during the deposition of the middle member. Molybdenum and vanadium were used as paleooxygenation proxies. What we see is molybdenum kind of varies and ranges between 0 and 6 parts per million. This would indicate that we have euxinic conditions throughout the deposition of the Ely Springs dolomite. However, our vanadium values contradict that. Vanadium values were typically negative throughout most of the formation, which would indicate that vanadium values fell well below the detection level of the ICP-OES. Low levels of vanadium actually indicate that we would have oxic conditions. So we have these two contradicting values. However, once again, the presence of sponge spicules, which is the proposed source of silica for the chert, would also indicate oxygenation levels. So the abundance of sponges and the low levels of vanadium suggest that our molybdenum values are incorrect, and this once again deals with barium, molybdenum, similar to barium, being highly mobile during diagenesis. Percent total organic matter averages relatively high, about 2% throughout the entire formation. This is particularly organic rich for carbonate rocks. A typical carbonate rock would average about 0.25%. So this is way above that. So this is a very organic rich formation. The chert is a little bit lower. The samples only average about 0.33%. And we do see an increase right here in the lower member. And we believe that during this time, how the ocean was more stratified, which led to, or aided in the preservation of total organic matter throughout deposition of the lower member. This ocean, the aiding of the preservation of total organic matter led to the increase in burial. And if this was a worldwide phenomena seen throughout many locations, this may have effectively removed carbon dioxide out of the atmosphere and may have been a mechanism to establish glaciation on Gondwana during a greenhouse world. Cluster analysis was also performed, and this was using past software. The data that we used were the 69 dolostone samples from Willow Springs Canyon. In particular, we looked at the enrichment factors for barium, copper, nickel, and zinc. We also analyzed the percent phosphate and the percent total organic matter. So these would all indicate increases in primary productivity. The results that we see is the separation of the data into 4 separate groups. The first group consists of samples that were occurred during the middle member. These were deposited during the Hernanian, and this was increased primary productivity that we saw in the primary or the middle member. The second group consists of samples that were deposited just below the oncolytic dolopaxstone layer, so that second interval of increased primary productivity, and a few samples that were at the base of the upper member. The rest of the samples generally fall into group 3, which indicates that there was low levels of primary productivity throughout these samples. However, we do have one outlier sample that is over here. This is actually in the Von Gulch limestone. And this one is an outlier. It had nickel concentrations that were approximately 20 times higher than nickel concentrations compared to any other samples. And the thin section revealed that it was actually probably a sponge that may have concentrated nickel concentrations due to the decaying process of the sponge. So that sample is considered an outlier and not considered further. The principal components analysis shows how these groups were then determined. So the first principal component analysis, or the first principal component, is plotted on the x-axis here, and that is the enrichment factors for nickel. The second principal component is our zinc enrichment factors. And we can see that percent total organic matter, percent phosphate, and enrichment factors for barium all plot close to the origin, showing that these weren't statistically significant in separating our 4 main groups. Samples from group 1, once again, these were the elevated primary productivity during the Hernanian. They were separated based on elevated enrichment factors for both nickel and zinc. Samples from group 2 were separated based on elevated enrichment factors for zinc. However, they were not quite as elevated as the samples from group 1. And we also didn't have elevated enrichment factors for nickel in group 2. And then group 3 plots all the way over here, indicating low levels of zinc and nickel. So this diagram just kind of shows all the data kind of squeezed into one big picture. What we see in the lower member during the early Cadian is we see an increased burial of total organic matter. Once again, this could have been the mechanism that effectively drew carbon dioxide out of the atmosphere, leading to the establishment of glaciation on Gondwana. A period of increased primary productivity occurs just below the oncolytic dolopaxstone layer. It is worth noting that upwelling probably was occurring throughout much of the deposition of this formation due to equatorial upwelling. However, upwelling was probably weak throughout most of the time, and with a stratified ocean, upwelling was probably upwelling warm, nutrient-depleted waters. However, as we reach the top of the lower member, we see this drop in sea level attributed to a global sea level regression, and we see a global cooling trend. This may have temporarily allowed upwelling to penetrate beneath the thermocline, allowing the upwelling of cold, nutrient-rich waters into the photic zone and allowing the formation of algal blooms. Sea levels then remain low, and we have the deposition of our oncolytic dolopaxstone layer. And this is once again supported by this increase in aluminum, titanium, and zircon just above the oncolytic dolopaxstone layer, indicating that we have this increase in detrital input. Our second period of primary productivity occurs during the deposition of the middle member during the Hernanian, and this is attributed to glaciation on Gondwana. So glaciation on Gondwana occurred during the Hernanian. We see downwelling of cool waters along the southern margin of Laurentia, or southern margin of Gondwana, which then allows the upwelling of cool nutrient waters along the western margin of Laurentia, leading to increased primary productivity. And then sea levels once again rise as glaciation concludes and melts. And when we see the second period of increased detrital input as we go into the Von Gulch limestone, the shallow water Von Gulch limestone. So conclusions. So the Ely Springs Dolomite records these large-scale sea level changes. We see that elevated sea levels throughout the lowermost portion of the lower member, and then we see this drop in those elevated sea levels as we reach the late Catian and the uppermost portion of the upper member, and this is once again due to a global sea level regression. Sea levels then remain low throughout the deposition of the middle member, and this is due to the establishment of glaciation on Gondwana. And then we see the subsequent rise in the deposition, or the rise in sea levels during the deposition of the upper member in the Landoveria, the earliest Silurian. The high percent total organic matter within the lower member may explain how we did establish a glaciation on Gondwana during a greenhouse world if the burial or enhanced burial of organic matter that we observe along the western margin of Laurentia was indeed a worldwide phenomenon. The positive isotopic excursion that we see in the middle member that reaches a value of 1.6 parts per mil is determined to be the HICE, the Hernanian isotopic carbon excursion. And with the identification of the HICE, we are able to more definitively place the Ordovician-Silurian boundary at the boundary between the middle and upper members within the Ely Springs Dolomite. We're also able to determine that upwelling did occur along the western margin of Laurentia, as hypothesized by Pope and Stefan in 2003. And this was determined by the enhanced enrichment factors for copper, nickel, and zinc throughout the deposition of the middle member during the Hernanian. Based on the short-lived nature of upwelling and increased primary productivity, we were able to support the hypothesis of Finnegan et al. That the glaciation was also a short-lived event and limited to the Hernanian and didn't stretch into the earliest Silurian. The rapid rise and then subsequent decline in the enrichment factors once again shows that we do have a rapid onset and quick termination of glaciation on Gondwana. And this rapid rise, or this rapid onset of glaciation and rapid termination of glaciation would drastically affect Hernanian fauna living during this time. And then finally, the low vanadium levels and the presence of sponge spicules throughout the Ely Springs Dolomite suggests that oxygen remained relatively high along the western margin of Laurentia, which supports that the second phase of the mass extinction may have been more due to climate deterioration as opposed to anoxia, if this is a worldwide phenomenon. So with that said and done, I'd like to go ahead and, well, first thank everybody for being here. So thank you. I'd like to thank my family, so my mom, my dad, that's them right there. I'd like to thank my brother, my boyfriend Spencer sitting over there. I'd like to thank all my friends back home in the great state of New Jersey. I don't know if you guys knew I'm from New Jersey. But
you've never mentioned it.
I know, I have not. So thanks to all my New Jersey friends. I'd also like to thank all my friends here in California and all the grad students here in California. Everyone has been just great and wonderful. I'd also like to go ahead thank all the faculty here. So if I did not personally thank Wayne, I don't think I would ever hear the end of it, so thank you, Wayne. I'd like to also thank Nicole for showing me how to use PAST and going over the statistical software, so thank you for that. Diane, who's not here because she introduced me to Illustrator, which has just become my life at this point. I'd also like to thank Brady, who brought me to Thailand, which was an awesome and amazing experience, so thank you. I'd also like to thank Dr. Kirby and Dr. Lloyd. Dr. Lloyd, I didn't have a picture with you, so I had to steal this from online. But
you could have just said you were off the frame.
Ah, this is true. This is true. Yeah. Oh, I like that. That's better. Yeah. But thank you both for letting me use your lab and agreeing to take this endeavor of my thesis. And last but not least, I cannot thank Adam enough for dealing with me for the past 2 years. It's been fun, and I'd like to thank you very much for all your encouragement and support and all the good times. So thank you.